Welcome to Acutherm's webinar presentation, System Application of Therma-Fuser VAV Diffuser Systems. We'll be ready to start in approximately 8 minutes. Thank everyone joining us for today's webinar, System Application of Therma-Fuser VAV Systems. This is a webinar in an ongoing series of webinars we've been presenting, so hopefully you've had a chance to attend one of the previous ones. If not, a quick summary here that we are talking about Therma-Fuser VAV diffusers, which are diffusers with a VAV damper and a thermostat built into them. By having a thermostat in each diffuser, you can create very small zones of control and provide very good comfort through individual selections of set points. Also, by having a VAV damper in each diffuser, it does produce a superior air distribution by constantly maintaining a very high discharge velocity even at low air volumes, and thus mixing the room quite well at all times. Primarily, the diffusers we're talking about are thermally powered, means they're not electric or pneumatic, no wires, no tubing, powered by the temperature of the air, both the supply air and the room air. We do offer individual set points, leading to thermal comfort, better air quality in the rooms. They've been proven to be very robust over the years. We have really a no maintenance requirement on them, other than really to keep them clean for presentation purposes, and a 10-year warranty on the thermally powered ones. I'll throw in there, we also have electric diffusers as well, and we will touch on those at some point. They're a great way to design a low energy system in addition to a very comfortable system, and we'll get into the system design here as today's webinar, and all of that leads to some LEED possibilities, and that's the subject of another webinar where we'll be presenting. So if you're interested in that, take a look at the website and you can sign up for that one coming up shortly. But for today, we're going to be looking at the application of the diffuser and designing the systems around the diffusers. So we'll start with sizing and locating the diffuser. We're going to get into the system design principles behind the system. Then we'll look at the zoning of the system for simultaneous heating and cooling. And we'll conclude by putting all that into practice with some system examples. First, sizing and locating of the diffusers. Nice answer here is you size and locate them as you would any diffuser. Kind of a cop-out answer, I know, but there are some benefits right off the bat here for VAV diffusers, and that is they may be oversized. You don't have to worry about that because they have a VAV damper and they're going to simply turn down to match the load in the space. Oversizing can also be a good design tool to use. So when you're working toward the end of the duct run and you're starting to run out of pressure, you can upsize the diffuser and get the same volume of air at a lower pressure. This technique can also be used if you're looking to design a very quiet system or the customer's placed a sound design criteria on you. By lowering the pressure in the system, you can lower the noise in a system, and then by oversizing the diffusers, you can still get the same air volumes, meet those design load requirements. Now, with any diffuser, you want to make sure you don't have that high velocity air hitting the occupants. So we recommend that the maximum velocity at any wall is the throw distance for that 150 feet per minute throw. However, you want to make sure you can maintain good room air movement when the system turns down. It is a VAV system after all. So it's also nice to place the diffuser where the lower at turn down that the 50 feet per minute throw distance reaches to the wall. And if you're working in a larger room, halfway between the distance between the diffusers, you can pretend they're wall and use those same rules, or basically doubling that 150 feet per minute throw distance between two diffusers. What does all that mean? Well, something I think unique to Acutherm is we do have performance charts that show not only the performance of the diffuser at the 100% open position or design condition, but also at the 25% open or the turn down condition. So you do have that performance data to use when selecting your diffusers. To put into example what we were what we were just talking about, I've pulled a performance chart here on the screen from our Model TF diffuser, just looking at a 10-inch diffuser there at a 0.15-inch static pressure. And what I'm looking at is under the maximum flow or the 100% flow condition, the 150 feet per minute throw distance is 8 feet. And then in the other column there, we look at what's the throw there, the 50 feet per minute throw at the turn down condition, and that's 10 feet. So ideally, this diffuser would be located 9 feet from a wall. Now I realize rooms aren't square. We don't always have a perfect 18 by 18 room, and very uncommon for the diffuser to get the center of the ceiling anyway. There's always lighting or sprinklers or PA systems that get into that ceiling first. So you're always going to make some compromise when locating a diffuser. My recommendation here is if you have to go a little bit closer to a wall, that's better than going a little bit further from a wall. My logic being that going a little bit closer to the wall means that when the diffuser is 100% open, you may have a little bit of velocity coming down that wall toward the occupants. But given this is the 100% open, that's your maximum load case, your design case, that's only going to happen a couple times a year. Where you spend the majority of the time is in a turn down condition. So we want to make sure that we are getting good mixing at all times. And so going a little bit closer to a wall is preferable to going a little bit further from a wall, in which case you might create less well-mixed rooms on the turn down case. Something that is unique to Therma-Fuser diffusers is because we have a thermostat built into the diffuser, you want to make sure that there's no obstructions near the diffuser that could reflect the supply air directly back onto that thermostat. We do use a positive induction mechanism to draw room air up into the diffuser. That's a subject of another webinar, but just keep in mind that no obstructions near the diffuser. So a minimum distance of 2 feet away with a wall or a beam or a light to prevent that that supply air from bouncing right back up into the diffuser and throwing off the room temperature measurement. If you do have to locate the diffuser near a wall or a beam or something, we do have directional baffles that can be put in to block flow from one side of the diffuser or two sides, or even like corner arrangements. So if you do have to squeeze that diffuser into a tight space, it's just a matter of getting some directional baffles and blocking the air on the sides where the obstructions are. The diffusers work very well in cooling up to ceiling heights of around 20 feet. But in heating, a little bit more challenging to get that warm air to blow down. We recommend 10 feet height preferred. You can get away as high as 12 feet, but really 10 feet preferred to make sure you get good room air mixing even in the heating mode. System design principles, our next topic. Really two key things to make sure your Therma-Fuser diffuser system works well, and that's taking a look at the pressure and the temperature within the system. So objectives of pressure control. Really, you need to provide enough pressure to achieve the required air volumes in the spaces. The diffuser itself will operate at pressures as low as 0.05 inches water gauge or 12 pascals, but you want to typically go a little bit higher than that because you're trying to achieve some kind of a design air volume in the space. So you want high enough static pressure to achieve your design air volumes, but you want to limit the static pressure. So these are VAV devices. They are going to open and close. The flow through the system is going to change. So you need a means of controlling the static pressure so it does not build up in the ducts when the diffusers head toward their minimums. Also, as any diffuser, it will become noisier with higher pressure. So our recommendation is to keep the static pressure around the 0.25 inches water gauge or 62 Pascal mark. That'll keep most of our diffusers around the 35 NC for noise, which is usually quite acceptable. And lastly, you don't want the pressure getting so high as to cause the diffusers to fail to operate. Around 0.4 inches water gauge, you can start blowing the diffuser open or preventing it from closing. So you definitely don't want the pressure to get that high. And lastly, we want to design pressure independence into the system. We may not know what the main system is doing, so to get consistent operation, we need a means to get another reason for getting some kind of pressure control onto our system. The diffusers themselves are pressure-dependent devices, so we have to design this into the system supplying the diffusers. So one of the best ways to do this, and when I say best, meaning the lowest energy method of doing this, is with an all-low pressure system and fan speed control. In this approach, the static pressure at the diffuser furthest from the fan is high enough to achieve our design air volumes. The duct design is such so that the static pressure at the diffuser closest to the fan is no higher than that 0.25 inches water gauge. And then as the diffusers start to open and close and work toward their minimum, we're going to locate a static pressure sensor downstream in the ductwork, usually 2/3 to 3/4 of the way downstream. And that's going to directly control our fan speed. So as the diffusers start to close toward minimum, the fan slows down, prevents the pressure from building up. And then when the diffusers open up again, the fan can ramp back up and keep that pressure available for the diffusers to provide the air volumes they need. That method not only always applicable to larger buildings, large footprints, or multi-story buildings. So another method is a part medium pressure, part low pressure system using modulating zone dampers. So in this approach, we've designed the low pressure duct sections similar to before, in that pressure at the last diffuser is high enough for design airflow, pressure at the first diffuser is no higher than the 1/4 inch. But now we have the static pressure sensor feeding back to a modulating zone damper. This could be an Acutherm PIM module or pressure independence module, or a converted VAV box, but a damper with a controller such that when the diffusers close toward their minimum, that damper can close down and prevent the pressure from building up. And again, when the diffusers open up again, the damper opens up, providing the air they need to supply the spaces. In the medium pressure portion of the ductwork, and in that drawing there, these might be 2 floors of a multi-story building, and that's the riser between them. But you'd locate another static pressure sensor there. Now, as multiple of these modulating zone dampers start to close down, the fan can slow down because by maintaining the pressure in the medium pressure section of the duct. So you're still achieving good energy savings by slowing down the fan. We're just using that medium pressure to distribute around the building the longer distances, and then dropping to low pressure amongst the diffusers. This can also be done with a bypass instead of a modulating zone damper. If you do have a constant volume system, then you have to use a bypass, got to keep the air going somewhere. So instead of that modulating damper being in line with the zone of diffusers, it's run between the supply and the return ducts, and now as the diffusers start to close toward minimum, that bypass would open up and keep the air flowing back around. Another option for a bypass is a relief ring or a relief collar. These are devices that create a bypass right on the diffuser. Now as the pressure at that individual diffuser starts to increase, air then gets bypassed into the ceiling. And these do require a ceiling plenum return system to operate, but they can be a very economical way to get a bypass into a constant volume system. A good option in some of those retrofit situations where there's no plan to ever put a VFD on the fan. That talks through the pressure control. Let's move on to temperature. So our objectives of supply air temperature control here are, 1, to provide a constant supply air temperature to the diffuser. Now that's not to say you can't reset the supply air temperature. It's just that what we're looking for is to reset to another constant temperature. The diffuser is trying to control the air volume to maintain temperature in the space. And if the supply air temperature is fluctuating too rapidly, the diffuser doesn't know which way to adjust the volume. So a step type function where a decision is made, a supply air temperature is selected, held for a while, and then later a decision is made to change to another selection works quite well if you're going to run a supply air temperature reset strategy. Also, we want to limit the supply air temperature. The diffusers use the supply air to determine whether they're in the heating or cooling mode. And for the thermally powered diffusers, these are fixed ranges. So they're in the cooling mode between 50 and 68 degrees. And they're in the heating mode once the supply air is above 80 degrees. But we try to say keep it as low as possible because you really shouldn't need too hot an air to heat a modern building with a good insulation these days, but they will operate as high as 120 degrees. Although the lower you can keep it, the better you are with stratification and being able to drive that warm air down. And lastly, we need a means to provide changeover between the cooling and heating modes. So the source of heating and cooling needs a means to know when to turn on the heating. As I mentioned, the diffusers are using the supplier to determine the mode, so we need something to make that decision for the system. So for our first two goals there, as far as a constant supplier temperature and to limit supplier temperature, a discharge air temperature sensor on our source of heating and cooling is the best way to do that. And if that's a modern, more sophisticated unit where you can modulate the cooling, modulate the heating, this works very well because you can pick your supplier temperature. The unit will control to that. And when you want to pick another one, it'll control to your new temperature. If you're working with older systems, retrofit situations, at a minimum, you want to make sure you have a cooling low limit just to make sure that the air doesn't get too cold, and a heating high limit, make sure it doesn't get too hot. Working with the bypass and the pressure control, we don't want that cold air looping back around and freezing the coil, or the hot air tripping the unit on high heat. So you do need some kind of limitation on there at a minimum, but if you can get that modulating unit on there, all the better, for better control, better comfort, and really better energy savings. For the third point, the means of changeover, at a minimum, we need a temperature sensor in one of the rooms. We don't like to recommend the return to the unit because that's an average of all the rooms, and you miss your peaks, your highs and your lows if you're sitting in the average. Not to say you can't put a sensor in the return from one of the rooms, though, because that's, again, not an average temperature. That's the one room. And it also doesn't have to be as simple as a single sensor. If you want, you can use multiple sensors and use a voting sequence on when to switch between the heating and cooling modes. If you start to look at some of our electric diffusers, which can be tied in over a BACnet network, that can be a great way to bring in the temperature from multiple rooms, run a voting sequence, and decide when to switch on the heating and cooling based on that data. Zoning. So you still need to zone the building well. The diffusers themselves can't create hot and cold air, so we need to do good zoning in our space so that we can provide heating when we need to and cooling when we need to. The one thing to keep in mind is with a Therma-Fuser diffuser approach, we are going to create larger zones that are then sub-zoned with the Therma-Fuser diffusers. Each diffuser having the thermostat and VAV damper built in allows us to create these larger zones. And what we want to do is create them by like usage and like exposure so that they're all similar to each other, and we can thus create them as one large zone and allow the Therma-Fuser diffusers to kind of create that individual comfort between the rooms or in the space. A great method to work with that's a very efficient, energy efficient method is multiple air handling units. This way there's no reheat. If we put on an air handling unit to cover the north perimeter, an air handling unit to cover the south perimeter, same for the east and west, and then a fifth on the interior, that means each area of the building has its own air handler, and if the north needs heating while the south needs cooling, you're not bringing any reheat on, you're just switching that unit over to the different mode. So that can be a very energy efficient approach. It doesn't have to be the classic 5 zones. You can zone the building by face. You can, for example, take the entire southern face of a multi-story building and create a zone that way. Or if you've got a narrow rectangular building, you might drop it to 3 zones because you've got stairwells in the ends or other spaces that aren't as critical and allow you to reduce the number of air handlers that way. Another method would be to use a separate perimeter heat system. This could be baseboard hot water, a separate ducted system. But with a separate system there, taking care of those skin losses, we can treat the rest of the building just as a single cooling zone and allow the Therma-Fuser diffusers to sub-zone that. Duct heaters, the very classic reheat approach. In this case, we are putting a duct heater on each of the faces of the building, and when that, again, as we spoke earlier, if the north needs heating while the south needs cooling, we can bring the heat on in the north while still running the cooling in the south. Not as energy efficient as some of the other approaches, just because we are doing reheat, but still a very common method today. We're moving along quite rapidly here. I notice I'm running quickly out of time, but if you do have any questions, please ask them at any time. Use your questions window in the GoToWebinar control panel. So let's conclude here with some system examples and kind of put everything we've learned into effect on some real jobs. This job was originally a VAV reheat job, VAV box reheat job. They were pneumatic boxes, 26 boxes, 58 diffusers, providing 26 zones of control. We redesigned this for a Therma-Fuser Diffuser approach. You can see the larger zones of like usage, like exposure. We've reduced it to 6 VAV boxes. Why are the boxes there? Well, number one, the VAV damper is providing our pressure control. This was a partial retrofit of a larger system, so no real control on what the house system was doing, but we're able to create those low pressure zones around the diffusers by using the damper in the VAV box to create our pressure control, and then using the coil in the box to provide the reheat. So while this used to be 26 zones of control, it's now 58 zones of control with the Therma-Fuser diffusers providing those zones throughout the building. Also can be a very cost advantage to go with a Therma-Fuser diffuser system. A lot of people have an idea that the VAV diffuser costs more than an old fixed diffuser, and that's true. But when you get into the system installed costs, it's the VAV boxes that are the majority of the cost in the system, not the diffusers or the ductwork. So in that previous example there, by reducing the number of VAV boxes to just what we needed for pressure control and to provide the reheat when necessary, we can really get some good savings out of this job. In this particular one, it was a 30% reduction in cost. VAV boxes, especially in retrofit situations, can be relatively easily converted to a Therma-Fuser diffuser approach. One, creating the static pressure control by using the VAV damper already in the box. A lot of times you can even use the controller that's on the box by porting the high side of the differential pressure sensor downstream in the ductwork, leaving the low side open atmosphere, and now you are measuring static pressure. Temperature control using the coil in the box. Again, great if you can get a discharge temperature sensor on it to control that, whatever that source of heat is, and then a room temperature sensor to know when to turn the heat on and off again. Here's an example of a system using multiple air handlers. In this case, it was a smaller library, 3 different RTUs on this particular job. You can see the first rooftop was serving the interior space in orange there. The second rooftop picked up that top and right perimeter of the building, and then the third one was on the left and lower face of the building. So an all low pressure approach, fan speed control here controlling the static pressure amongst the diffusers, and then because it is zoned by separate rooftop unit, no need for reheat. The heat or that whole zone going into heating or cooling as required. Room temperature sensor in there, providing that decision on when to switch between heating and cooling. I mentioned earlier, not an approach limited to small buildings. This is a multi-story little office building you can see there, and they've used 6 different air handlers in this case to zone the building, 1 for each face of the building. Again, to avoid the need for reheat. And in this particular instance, they split the interior into 2. And again, a very effective and energy efficient approach. Because this is a multi-story building, though, it's not an all low pressure approach. There'd be a modulating zone damper on the takeoff to each floor. The ductwork on each floor then being a low pressure zone, medium pressure up and down the risers, and fan speed control to maintain that medium pressure section. Example here of a separate perimeter heat system, and I realize that drawing's a little hard to see, so let me eliminate a bunch of it. It was originally laid out as a VAV box project, and we converted that to a all low pressure Therma-Fuser diffuser approach. In this particular instance, though, again, with the separate perimeter heat taking care of the skin losses, we can approach this just as a cooling only zone, or if you need morning warm up, that works too in this approach. And in this particular example, the customer told us they had some tight ceiling restrictions. So we also laid it out as a part medium pressure, part low pressure, whereby we've got multiple zones per floor, modulating volume dampers to control the pressure in each space, and then those medium pressure sections of duct to distribute the air around the floor. My last example here is an interesting one because it's a building with multiple exposures, but yet it only has a single air handling unit. This building is a very energy efficient building and a very good example of the LEED process working as it was intended. All parties were able to talk about how they're going to design this building before it was started, and it was a retrofit of an older building. And the decision was made early on to add better insulation to the building, better glass, better roof insulation. And they did it such that when combined with the zones of control provided by the Therma-Fuser Diffuser, they could treat this building as a single zone, even though there are multiple exposures on it. So a combination of good insulation and the subzoning of the Therma-Fuser diffusers allowed this to happen. It's an all low pressure system. So fan speed control, controlling the static pressure to the diffusers. And then without that, because it is a single zone, no need for reheat. The building will bring on some morning warm up when it needs it and either go into ventilation or cooling the rest of the time. That particular building, very energy efficient, as I mentioned. At the time of its construction, it was one of the first LEED Platinum buildings under the NC 2.2 rating scale. It also possibly more impressively bettered California's stringent Title 24 energy codes by 45%. And more recently here, it was recertified under the newer LEED version 4. And it was the first platinum building in the world, this time under the existing building section of the LEED system. So still a very energy efficient system many years after construction. So that was today's webinar. We looked at sizing and locating the diffuser. We touched those system design principles about providing pressure control of the system and supply air temperature control. Looked at how to zone our buildings and then put all that into practice with some system examples. I'd like to remind everyone we do make a full range of Therma-Fuser VAV diffusers from square, linear slots, that's ceiling and sidewall, round diffusers. We do have the electric diffusers. If you're going to tie it all back together into a building automation system, back then on board each of those diffusers. We do have a variety of options and accessories, including, I mentioned the pressure independence module, if you need a modulating zone damper, or some duct heaters, if those help you design your system. Our next webinar is on LEED and how the Therma-Fuser system design can help with LEED credits. That'll be on May 17th, so check out the website and sign up there. And I'm really running short of time, so I'm going to quick throw out some names here. If you do want to discuss a project, any of one of these folks would be happy to work with you and just see what a Therma-Fuser diffuser might look like on your project. And I do have a couple questions that I want to touch on before we run out of time here. So I'm being asked where are Therma-Fuser diffusers applicable and where not applicable. Well, they are a VAV diffuser, and they'll work typically anywhere a VAV system will work. So something like a hospital in the U.S. where there are requirements for pressurization and air changes per hour, typically not a typical VAV application and not a good application for a Therma-Fuser diffuser. But a medical office building, great application. Those buildings have lots of small offices, exam rooms, and being able to provide those small zones of control that the Therma-Fuser can provide is a great way to design those buildings. I've got time for just one more question, and anything else coming in, I'll be happy to take after the fact, or you can, as I say, contact any of these folks and they'll answer your questions. I'm being asked about the adaptability to different ceiling types. So most of the Therma-Fuser diffusers are designed for a lay-in type ceiling, but we do offer adapter frames and trims so that we can put it into almost any ceiling. If you're working with a Don Fine line, an Armstrong bolt slot, metal pan, we have options for almost every ceiling you can think of. Please just give us a call, and we can tell you the best way to approach the ceiling you're working with. All right. If there are no further questions, then I'd like to thank everyone for attending, and I know your time is valuable, so thank you again for joining us, and this will conclude our webinar, System Application of Therma-Fuser VAV Systems. Thank you.